Keeping in mind the significance of the equilibrium and equilibrium constant, we will discuss few more numerical problems so that this concept becomes very clear. Now let us take another question. The question is, in the gas phase reaction 2A plus B going to 3C plus 2D, it was found that when 1 mole of A, 2 mole of B and 1 mole of D were mixed and allowed to come to equilibrium at 25 degrees Celsius, the resulting mixture contained 0.9 mole of C at a total pressure of 1 bar. Calculate the mole fractions of each species at equilibrium. The value of Kx, the value of K and delta Rg naught. Let us see how to approach this question. 2A, this is the chemical reaction, 2A plus B in equilibrium with 3C plus 2D. And the given information to us is that you are mixing 1 mole of A, 2 mole of B and 1 mole of D. You mix A, B and D and then you allow the reaction to come to an equilibrium, and eventually when you are mixing A, B and D, C will be formed and the equilibrium at some point will be attained. So what we will do is, we will list A, B, C and D. Initial amounts. What are the initial amounts of A? 1.0, 2.0, initially C was nothing and D was 1.0. And then it is given that at equilibrium C was formed, 0.9 mole of C were formed. So if I write at equilibrium 0.9 moles of C were formed. So what is the change if I calculate change? How much will be the change for A? If you look at here, 2A forms 3C. Therefore, the amount of change in A will be equal to 2/3 of the amount of change in C. Because 2A is forming 3C, therefore, the amount of change in A will be equal to 2/3 of the amount changed in C. Since the amount changed in C is 0.9, 2/3 of 0.9 is 0.6. That is 2/3 of 0.9. And for B it is 1/3. 1/3 is 0.30. And for C anyway the change is same because there was nothing in the beginning. And for B also 2/3 of C is the change. Let me put negative and negative here, positive and positive here, because these are reactants. These reactants are consumed and product is formed. Therefore, at equilibrium, number of moles, this will be 0.4, this will be 1.70, this will be 0.90, this will be 1.60. So I hope these calculations are very clear. It is very important to understand how we arrived at these numbers. Now let us go back to the slide and look at the table. We have calculated the equilibrium amounts in terms of number of moles. A is 0.4, B is 1.7, C is 0.9 and D is 1.6. The total addition of all this is 4.6. And once I know the equilibrium amount and total number of moles, I can calculate mole fraction, because mole fraction will be the number of moles divided by the total number of moles. That is 0.4 divided by 4.6 will come out to be 0.087 in this case. 1.7 divided by 4.6 will be 0.37 in this case. 0.9 divided by 4.6 is going to be 0.196, and 160 divided by 4.6 is going to be 0.348, and of course when you add all the mole fractions, this has to come to 1. So we have calculated the mole fractions at equilibrium. And immediately we can calculate Kx. Kx will be equal to mole fraction of C raised to the power 3 into mole fraction of D raised to the power 2 divided by mole fraction of A square into mole fraction of B. And once you substitute these numbers, we get a value of 0.33. Kx we have been able to get 0.33. If we have Kx is equal to 0.33 and the reaction is 2A plus B in equilibrium with 3C plus 2D and we just in the previous lecture we derived this equation K is equal to Kx into P by P naught raised to the power delta nu. And can I write this as Kx into P by P naught raised to the power delta nu will be 3 plus 2 is 5, 5 minus 3 is equal to 2. Now if I know the total pressure at equilibrium and I know the value of Kx, I can get the value of K. Kx is known, and if P is 1 bar, then K is equal to Kx. And this is the condition which is given to us. Let's go back to the slide. We derived this in the previous lecture and we just discussed that when P total pressure is 1 bar, P naught is anyway 1 bar, K will be equal to Kx. Therefore, the value of K comes out to be 0.33. If we know K now, immediately we will be able to calculate the standard reaction Gibbs energy, delta RG naught. Delta RG naught is minus RT log K. You substitute the value of R in appropriate units, the value of T and log K, we get overall value 2.8 kilojoules per mole. delta R G naught at this composition, that is delta R G naught, actually this is the standard reaction Gibbs energy, turns out to be positive in this case, because the K value is less than 1. That is why delta R G naught turns out to be positive. So, this question describes that how you can make use of the information on just the amount of one of the reactants or one of the products to calculate the amount of the other species present at equilibrium. And once you know the amount of each species present at equilibrium, then you also know the total amount. You can calculate the mole fractions, and from the mole fractions one can calculate Kx, and once you have Kx and the total pressure information, you can calculate the value of K. Let us take another question now. The question is, the equilibrium constant of the reaction 2C3H6 gas forming C2H4 gas plus C4H8 gas is found to fit the expression between 300 K and 600 K. Log K is equal to minus 1.04 minus 1088 by T in Kelvin plus 15.1 into 10 to the power 5 by T square in Kelvin square. Calculate the standard reaction enthalpy and standard reaction entropy. This question again describes the effect of temperature on equilibrium constant. And Vant-Hoff equation is a very useful equation in dealing with such questions. Vant-Hoff equation is d log K by dt at constant pressure is equal to delta R H naught by RT square. Another form of this equation I can write dou log K 1 by T instead of T. Let me write 1 by T at constant pressure, it will be minus delta H naught by R, because d1 by T is minus 1 by T square, and eventually that will then convert into this form of the equation. Why I have transformed into derivative with respect to 1 by T is because the given information to me is log K is equal to minus 1.04 minus 1088 Kelvin divided by temperature plus 15.1 into 10 raised to the power 5 K square. These are K, Kelvin is introduced to get rid of the unit, is T square. What I have is T in the denominator. That is why if I differentiate with respect to 1 by T, it will be easy. Now let us differentiate this with respect to 1 by T. D log K d 1 by T. What will I get? This is 0, and the next one is minus 1088, because d 1 by T of T is going to be 1, and here it is 1 by T square. It will be 2 into 15.1 into 10 raised to the power 5 divided by T. This is what I am going to get when I differentiate with respect to 1 by T. Let us, and of course it will be Kelvin. Let us go back to the slide. what I have discussed is that d log k by d1 by t is minus 1088 plus 2 into 15.1 into 10 raised to the power 5 by t into k. So once I substitute the numbers, and let us see, go to the slide, and what do I get? I get, let me just correct over here, d log k d1 by t minus 1088 plus 2 into 15.1 into 10 raised to the power 5 by t, and this t is in Kelvin. We will put the information over here. Look at the slide. Once you substitute the number, the standard reaction enthalpy comes out to be plus 2.77 kilojoules per mole. Once I have standard reaction enthalpy, I can calculate standard reaction entropy from delta G naught is equal to delta H naught minus T delta S naught. And once I use that and write, look at the slide, delta R S naught is equal to delta R H naught minus T R delta S naught divided by T. This I am getting from delta G naught is equal to delta H naught minus T delta S naught. And you rearrange this, delta S naught will be equal to delta H naught minus delta G naught divided by T. And if we look at the slide, then after you substitute the numbers, we will get a value of delta S naught is equal to delta G naught can be calculated from minus R T log K. And we have been given the expression for log K. Once you calculate the log K at a given temperature, so what you do is calculate log K at T is equal to 400 Kelvin, and that information we can substitute over here. Once you substitute over there, what I will have is delta R S naught is equal to delta H naught, we just calculated, is 2.77, and delta G naught from minus RT log K will come out to be 9.37. These are all in kilojoules per mole divided by 400, and this is in kilojoules per mole. Once you solve this, this number will come out to be minus 16.5, and convert into joules. Of course, there will be Kelvin here, per Kelvin per mole. We get the reaction entropy also. Now we take up another question. Calculate the equilibrium constant of the reaction carbon monoxide gas plus hydrogen forming H2CO. Given that for the production of liquid formaldehyde, the standard reaction Gibbs energy is 28.95 kilojoules per mole at 298 Kelvin, and that the vapor pressure of formaldehyde is 1500 torr at that temperature. How to solve this kind of question? We have been given the information on the standard Gibbs energy of production of liquid formaldehyde, and we have been actually asked to find out the equilibrium constant for the formation of gaseous formaldehyde. So we will make use of this expression. Let us take a look at it. The standard Gibbs energy of formation of gaseous formaldehyde will be equal to the standard Gibbs energy of formation of liquid formaldehyde plus the standard Gibbs energy of vaporization, because the liquid has to be converted to vapor, of the formaldehyde. Once again, the standard Gibbs energy change for the formation of gaseous formaldehyde will be equal to the standard Gibbs energy of reaction corresponding to the liquid formaldehyde plus the corresponding standard Gibbs energy change for the vaporization. And this is the vaporization process, H2COl forming H2CO gaseous form, and for this the equilibrium constant we can immediately write as P by P naught. We have been discussing for a long time how to write the equilibrium constant. P is the pressure of H2CO and P naught is 1 bar, and once we know, we can immediately substitute this information into delta G naught is equal to minus RT log K. P is 1500 torr and P naught is 750 torr in terms of torr. And once I calculate, the number comes out to minus 1.72 kilojoules per mole. Therefore, for the reaction carbon monoxide plus hydrogen forming H2CO gas, we use this equation and substitute the numbers. The standard Gibbs energy for H2CO liquid is 28.95 given, and the standard Gibbs energy change for the corresponding vaporization process is minus 1.72 kilojoules per mole. Thus, the overall reaction Gibbs energy for the asked reaction turns out to be plus 27.23 kilojoules per mole. And once I know the standard reaction Gibbs energy, I can immediately calculate the value of equilibrium constant by substituting the equilibrium constant into delta R G naught is equal to minus RT log K. And K turns out to be 1.69 into 10 raised to the power minus 5. So note the tricks used in solving this kind of question. Initially, we were asked to find out the equilibrium constant for this reaction, formation of gaseous formaldehyde. And the given information to us is the standard Gibbs energy for the production of liquid formaldehyde. That means we must then add the thermodynamic quantity corresponding to the vaporization process. That is why we wrote this equation, that the standard Gibbs energy change for the production of H2COG will be equal to the corresponding standard Gibbs energy for the production of liquid formaldehyde, and somehow we calculate the delta G naught for the vaporization. Vaporization reaction, all of us very clearly understand, it is liquid conversion to vapor, and then we made use of the value of equilibrium constant to get the value of delta G naught, and used all this kind of information to get the standard Gibbs energy change for the given reaction. And once we had the information on standard Gibbs energy change, we were able to calculate the value of equilibrium constant. So what we notice here is that equilibrium constant depends upon the temperature, and it will depend upon the temperature only if the standard enthalpy of the reaction is a non-zero number. And then if it is a non-zero, the equilibrium constant might increase or it might decrease with rise in temperature, depending upon whether the process is exothermic or the process is endothermic. And you might have noticed that while solving many of or some of these questions, we made use of state properties, the properties of state functions. So therefore, when we are trying to optimize a process in industry, it is very important to understand the thermodynamics of the process, because the thermodynamic parameters accompanying the reaction, accompanying the process, it gives us direction, it gives us guidelines to optimize the process so that the given plant gives a maximum yield of the product. So I hope that these questions helped in understanding further about how to improve the value of K and how the external factors affect the value of K, and if the value of K is not affected, how it affects the equilibrium composition. Thank you very much.